in this lecture, in fact, from this lecture onwards, we are going to talk about synthetic carbon production. So here we'll talk about synthetic graphite. Now, I told you in the previous lecture that we need a lot of graphite for various applications. We also need this material in high purity. Natural resources may be limited. Sometimes also the processing of the ore can become very expensive. So we also need to have certain methods of artificially producing graphite. Now, unlike other metals, for example, or other elements, it is actually possible to make carbon materials artificially. So you cannot really make artificial iron or artificial gold, but you can make different forms of carbon, because we know that the source of all the carbon, even the one that we mine, the source of it is organic material. It is actually the organic material converted into carbon, because all the non-carbon atoms, they left the material at some point due to extreme conditions. Now, can we actually induce these extreme conditions? And then can we get the carbon? If yes, if we get the carbon, then what is the type of that carbon? Can we always get graphite? Or can we get diamonds, or can we get any other type of carbon? So this is something which is very interesting, and it will form a major section of this course, in fact. Okay, now before I start with the synthetic carbon production, I had in the previous lecture mentioned that graphite is a semi-metal. So what is a semi-metal? When any material, so first of all, you divide elements into 4 types. Insulators, then semiconductors, and then within the conductors you have metals and semi-metals. Semi-metals are basically, if you see the band gap, what happens is they have either very small or no overlap between their conduction and valence band. So for example, in the case of graphite, you have also, you can see this in this picture, you have a completely filled valence band and you have empty conduction band, but they touch at the Fermi level. So these kind of materials are known as semi-metals. There are other examples as well, some other elements, I think antimony, there is a certain type of tin. Also there can be certain compounds which are semi-metals. So now in terms of physical sense, you have basically some properties which are like metal. So graphite, for example, it's conductor. It also has a shiny surface. But on the other hand, there are also some properties which are not like metal. So you cannot, melt and mold or form your graphite. This is how it is. This is important also for manufacturing applications, because we cannot use what we use for metals. You cannot have the same elasticity. You can also not do manufacturing in full fibers out of graphite. So this is important for us. This is just for your information. Okay, now coming to the synthetic graphite. So there are 4 major techniques, and sometimes you use the mixture of these techniques, but 4 techniques that you can use for making synthetic graphite or making graphite. First of all, you can do heat treatment of pre-processed petrochemicals. So petrochemicals is a completely different subject area. You have so many different organic materials. Not just petroleum, not just the diesel and petrol. You also have so many gases. You also have certain other high carbon residues. High carbon residues will contain what is known as coke and pitch. These are some of the materials which are also used in different applications, but they can also be used, or at least some of them can also be used to give you carbon. So organic material, when you heat it, then you can remove all the non-carbon atoms and you can get carbon at some point at certain high temperature. Okay, now which organic material? Which one should you choose? You should choose something which has already a high carbon content. Now, not just high carbon content. If you want to get graphite, then you should also have certain possibility of having crystalline structure, similar to what you have in this. An anisotropic crystal structure should be possible. Okay, so we can take these petrochemical precursors and we can heat them, and then we can get graphite out. But that's number 1. Number 2, when we make steel, iron and carbon is mixed. Now, often it happens that if there is some additional carbon, or there are certain certain reactions that lose carbon within, when you're forming steel, then that carbon precipitates out. Precipitates means either it will deposit on, onto the surface, or it will just basically it will come out of your steel. So that is also interestingly often in a very crystalline form. Now why so? Because, well, you have this, there are a lot of small carbon units which are getting together, and the most stable form is anyway graphite. So they end up forming graphite. So this type of graphite industrially is called Kish graphite. We are going to discuss that most likely in the next lecture. Okay. Heat treatment of polymers. So I said heat treatment of petrochemicals, and then heat treatment of polymers also. There are minor differences, because when you're heat treating the polymers, in terms of the process, you have pretty much the same processes, but in terms of how should your what should be the structure, chemical structure of your precursor, in the case of polymers, you need to learn a few different things, and not all polymers will give you graphite. So this is the third method that we'll talk about. And the fourth one is making carbon from hydrocarbon precursors, gaseous precursors. So you can actually deposit carbon also by cracking the hydrocarbons that are in their gaseous form, like methane or acetylene, and then you get these layers of carbon, and then how do you get graphite from that is what we are going to learn. Okay, so now few other things. In all of these cases, the graphite that you will get in its polycrystalline form, but on the other hand, you also know that graphite crystals are not too large. Unlike other materials, you have relatively smaller crystals. So anyway, for most of the manufacturing applications, the graphite that you're going to have is going to be in its polycrystalline form and not a single crystal form. Okay, now this also we had discussed previously. For manufacturing applications, it's difficult to machine any carbon material because of not just their hard and brittle nature, because also you don't want to compromise on the crystal structure of the graphite and so on. And today we are going to see what is the solution to this. So we find it difficult to machine carbon, okay, and also because you have this anisotropic structure, then you cannot give complex shapes to graphite, because you have these layered structure. You cannot really bend it, or you cannot, without compromising the crystal structure, you cannot really give it if you cannot give it random shapes. Okay, and other things, it does not melt, it sublimates, you know that. So you cannot use a lot of manufacturing techniques also. Sintering or any kind of crushing techniques also cause a loss of crystallinity and also induce defects, so that is undesirable. What is the solution? Solution is that we make the graphite and other carbon materials from the organic precursors. So is it possible now? These precursors are polymers, for example, or petrochemicals also. They may be in semi-solid or solid state. So can we actually shape them and then do the heat treatment? So what we get in the final material, what we get in our graphite, is already in that shape. So that is actually what is most often done. So we already know the shape, and then we pattern our polymer in that shape, and then we convert it into graphite. And now that is interesting. How do we do that? This is one example. What we can there's one also option is that you can take graphite precursors, you can mix them into a certain binder. So either you can take the graphite precursor directly and give it a certain shape, or you can also, if that is difficult, let's say because it has not the best viscoelasticity or viscosity, not the optimum one. So in that case, we can also mix it into certain other organic polymer, for example a resin, and then we can convert it again into carbon. So this is basically you're mixing the different four techniques that I have discussed. So okay, we'll talk about that when we come to it. Now an interesting part is that now when you learn about graphite or graphite related materials, there are certain definitions that you need to know. That in fact, that is where all the confusion comes from in the field of carbon, that because people don't know these definitions. What is graphitic? What is graphitizing material? What is non-graphitizing material? And what is graphite? And what is graphene? So these are the definitions that you need to know, because only then you will be able to differentiate between the materials that you have. Otherwise, you may end up calling something graphite which is not really graphite, and then you will be contributing to the confusion. So, okay, in the next slide, so we are going to learn about some of these definitions. So, graphite, graphitic, graphitizing, and non-graphitizing. These are the definitions that I have listed on this slide. I'm not going to discuss each one of them individually, because you can just read through what I have written here. One thing I must definitely tell you is that these definitions of most of these definitions I have taken from what is known as IUPAC Gold Book. So you know what is IUPAC. IUPAC is what decides all the names for organic materials and carbon related materials. Now, what is this IUPAC Gold Book? This is where you find all the definitions, and you can easily do an internet search and you can find the definition. So whenever you have any confusion, if you think that, even if you're reading a research article and somebody says I have made graphene, but you look at the spectrum or you look at the data and like, no, this is not really graphene, or this is not really graphite, I wouldn't call it graphite. I probably would call it graphitic or graphitizing. So now if there is any confusion, just have a look at the IUPAC Gold Books. So IUPAC is International Union for Pure and Applied Chemistry. And this is the sort of agency that determines, that establishes a name. Now, you might also say that what is in the name? It's just about terminology. I've heard it from many people. It's like, yeah, I made what I made, and what is in the name? Let me give you an example. Right now, we have this coronavirus pandemic going on. Now, if there is some company which comes up with a drug which really has nothing to do with coronavirus, maybe it is some just immunity booster or something like that, something like lemon juice. Now, if that company gives it a name, some kill corona, although it doesn't have anything to do with the coronavirus, that can create a lot of confusion. Many people may end up buying it just because it's called kill corona. Now, the company might say that, no, I have nothing to do. I'm not claiming that I'm curing coronavirus. This is a name. What is in the name? No, it doesn't work that way. There is something in the name, because with the, if you give confusing names, then that is something that you're intentionally doing. And then you are, this is not a good thing to do, right? This is not, I will not go so far that it's ethical or unethical, but if you're knowingly creating confusion for example, a lot of companies are doing that with graphite related materials, because they call something graphite, which is not graphite at all. Which may just be a graphitic material. And graphitic material, you see that if you read these definitions, graphitic materials, as long as you can detect the peak for graphitic regions, you can call it graphitic, but that doesn't mean it is graphite. It may actually be a disordered carbon material. So there is a lot of confusion because of the commercial reasons, and it may also be for certain scientific reasons, because certain materials become too too popular, and then everybody wants to say that this is what I'm working on. So be careful. You need to go through these definitions, however, because we will need them for in whatever lectures we are going to then we are going to learn. Okay, so now I come to the first method that we discussed about making the graphite from petrochemical precursors. Okay. What is a precursor? Precursor is anything that that is your initial material. That is what you're going to heat, and then you're going to get your final material. Okay, this any non-carbon atoms are removed, you can get carbons. Not necessarily graphite, but some sort of carbon. Okay. Now, certain materials, for example, petroleum products such as coke, tar, and pitch. You know what is coal tar. And you probably know what is a pitch, but I will show you some pictures, maybe that will make it clear. So coke, coal tar, and pitch, these are some petroleum products which already have pretty high carbon content. So they have often very complex molecular structure, because they are a mixture of a lot of hydrocarbons, a lot of things that are almost carbon but not completely carbon. No, the hydrocarbons also over time degrade and they get fragmented, they get they make smaller hydrocarbons, and then some of them are so small and volatile that they they come out as in gaseous form, and then we still have these solid residues with very high carbon content. Some of them are in solid form, some of them are in liquid or semi-solid form also. These can be used for making graphite, so we just need to give them a little bit of push and then they will convert into the purer carbon forms. Okay, now here is a picture of coke. So this is how coke or processed coke looks like. We do a certain process known as calcination. Calcination is also a heat treatment, but you may have some air in the case of calcination. Air means you can have some oxygen. So there may be certain burning that is taking place. Now you may want, you're basically trying to burn out the organic impurities. So this, after the calcination, you get this kind of raw material which is known as petroleum coke. Okay, now coke in itself is a non-graphitic solid. So if you have read the definitions that I gave you before, what is non-graphitic? That means you cannot, when you do its characterization, let's say you do X-ray diffraction studies or something, characterization techniques we are going to learn separately. So when you do the characterization, you will not see the peak for graphite. That is what is meant by non-graphitic solid. In the beginning it is non-graphitic, and what we do, however, is we heat treat it to convert it into graphite. So it can be converted into graphite. This means it is graphitizable. So it is non-graphitic to start with, but we can potentially convert it into graphite by heat treatment. That is why we call it a graphitizable solid. Okay. Now when we do this pre-treatment of coke, as I mentioned already, that we do certain calcination processes, for example, also a little bit of refining and so on. Then the raw material that is our initial raw material. So this is the first raw material is what you get from your petrochemical refineries. But after that you also need to do certain pre-processing to get your actual raw material that you're going to use, which is known as the needle coke. Also, when we separately discuss raw materials, maybe we'll go into more details. So today our goal is to learn how to get graphite out of these precursors. Okay. Other than that, you have something known as pitches. So pitches, you've seen the roads. When you see a road construction, you have this what is known as damer, also known as asphalt. So this bitumen, the asphalt, that is what is basically your coal tar pitch. So when on a very hot summer day, you can also see on on the road sometimes a little bit of this pitch comes out. Now you know that this is a very, very viscous, black, nasty smelling liquid. That is what actually can be used after processing for making graphite. But not all kinds of pitches. So again, you have something called isotropic pitch. You have something called mesogenic pitch. Many of them are classified as just petroleum pitches. And then you also have something known as mesophase pitch. And this mesophase pitch is what is primarily used for making graphite. Isotropic pitch is also used for making carbon, but that carbon may not be graphite. So in the case of graphite, our 3D crystal arrangement is very important to us. Okay, so now these liquids, so also there is another picture of pitch that I have shown. This is almost solid. So the mesophase pitch, for example, its melting point is, I think, around 300 degrees, 300 degrees centigrade. So that means it's a very high melting point solid, almost solid-like material. So pitches come in various viscosities, and these are our raw materials for getting graphite. Okay. Also, pitches are used for making carbon fiber. So you see, they are very highly viscous liquids. You can already see when you see the road making, then you see that when they pour this on the road, the pitch on the road, then you see that there are long fiber-like things coming. It's like honey. It's very viscous. Has high viscoelasticity. So this also, of course, can be used for making carbon fibers, and in fact, it is used for making carbon fibers, graphitic carbon fibers. or isotropic pitch is used for making just carbon fibers, not graphitic. So this is what we do with the different pitches. So yeah, here is the definition of mesophase pitch, the one that we use for making graphite. Why? Because it has already certain graphite crystallites kind of floating in it. These are already anisotropic. That means they have this graphite-like structure. They have the layered structure. Isotropic means it will be same in all directions, but this already has a preferred direction, let's say. And these are even optically detectable. It's more like, so this material is more like what you know as liquid crystals. So you have crystals, but they, all together they have a certain flow, so you will not call it crystalline solid. So that is your mesophase pitch. Isotropic pitch, on the other hand, does not have these kind of graphite-like crystals. Okay, now, yeah, I already told you the answer to this question. I thought I will ask you which one should be used for graphite production. So now you know it's mesophase pitch. Okay. Now there is this, what do we do with, let's say, coke or pitch, but pitch, because it is a little bit viscous, so we are rather going to use it for making fibers. So I'll cover the fiber fabrication in the carbon fiber section, so that then we'll talk about the mesophase pitch and so on. Now let's talk about needle coke particles and how do we make something out of it. So I mentioned to you that you can already give a shape to your precursor when you want to make something out of graphite. So this is what we are going to do. But even your precursor, the needle coke, that is in the form of granules, or in the form of big lumps, or not powder, but you have particles, grains. So now what do you do with these grains? Okay, so you want to heat treat this grain, and then you know that you will get graphite out of it, but you need to bind these grains and give them a certain shape. So what you do is you take a certain type of resin, which is also a high carbon containing resin. So as I mentioned, I think before, that resins are very viscous polymers, epoxy resins. You may have also heard of epoxy glue. You get, so especially for a lot of research purposes, you will get something called epoxy glue, which is nothing but a very, very, very viscous polymer. And sometimes you also have two components of this glue. One is a polymer, one is the cross-linker. So when you mix these two things, then this polymer gets cross-linked, and that becomes hard. So then that serves as your glue. That is also a type of epoxy resin. So what you do is you take your needle coke particles, which may be of random shapes, these grains, and now you want to, for example, make a cylinder out of it. You want to make a graphite rod. Graphite rods are used as electrodes. Okay, so what do? You now give it a shape of a rod. So let's say I take a cylindrical, some pot, and then I put my resin and as well as the coke particles, and now this resin is cross-linked. Cross-linked means you want to harden it. Cross-linking basically means that you have different polymer molecules that are attaching to each other, and the overall material becomes hard. That can be done by by adding another chemical, which is your cross-linker. It can also be done by just heating. Certain polymers have a chemical property that by heating they will convert into certain radicals, and then they will attach with each other. So that can lead to hardening. Some we'll also learn about some polymers that can be cross-linked by the exposure to the UV light. So these are known as photoresists, and this is what we use in photolithography. So there can be many ways of cross-linking the resin, but the idea is to harden it. So you will give it a certain shape. You mix your coke particles with your resin or pitch. Even sometimes instead of resin you can also use pitch. It depends on which type of pitch and also the viscosity of the pitch. If it is optimum, then you can also, so you will have a certain liquids because you need to give it a shape. Okay, now you first heat treat it to up to, let's say, 1200 degrees, between 1000 and 1200 degrees. Typically most of the non-carbon atoms, or they will in principle leave by 700 degrees. Now, I'm saying most of them, not all of them. So at 700 degrees, most of the non-carbon atoms go away, and then you have carbon-carbon bond formation, and that around 900 you will get, let's say, 98% purity in your material. That will also depend on the size of your shape. If you have a very thick sample, then you can imagine that it's very difficult for the impurities sitting at the center. If you have a very thick sample, central impurities will find it very difficult to go out, to anneal out. So you need also the surface area. There are many things. So in the case of carbon fibers, things work differently because you have much higher surface area. So it's easy for the non-carbon atoms to anneal out in the form of certain volatile small hydrocarbons or gaseous forms. Okay. Now you heat it. The first step is to heat it up to, let's say, 1200 degrees, but in the presence of inert atmosphere. So now we are going to do most of the things in the inert. So with the calcination process in the beginning we did, where we we just pre-processed our coke, but now on we are going to mostly work under the inert atmosphere, and that is why it is not a burning process at all. Heat treatment is the best option. Whenever you are confused whether you should call it burning or calcination or whatnot, just call it heat treatment, because that is never wrong. Okay, so now you will get some sort of your carbon material. However, this carbon material will still have impurities, and what it will also have is pores. Why will you have pores? Because all the non-carbon atoms or whatever, there is some mass loss, net mass loss from your material, right? So how will that mass be lost? You will either have the entire thing will shrink, or you will get some porosity. So in this particular process, you will typically get, because also you have sort of non-uniform things. You have coke and you also have a resin or pitch. So it's already a mixture of the two materials. So you'll typically get pores. Now what do you do? How do you fill these pores? Now you have, think about it, you have a carbon structure with pores, and now you want to fill those pores, but with carbon itself. So what you're going to do is you're going to again take another resin, maybe this time with a lower viscosity, so that it can get filled inside the pores. And now you will carbonize it again, but this time you will carbonize it now above 2200 degrees. In most industrial processes, 3000 degrees. So again in the inert atmosphere, and this time what you're going to get graphite. In any case, at 1200 you would not get graphite. You will get certain form of carbon which may be graphitizing carbon, but it's not graphite yet. And graphite you will only typically get about 22 degrees. So now you will heat treat it again in the inert atmosphere in order to ensure that there is no burning. Okay, now this resin filling you can do actually multiple times, depending upon how many pores do you have and how complex is your shape and how big is your shape and so on. So you may have to do it more than once, and then also that will determine the quality of your graphite. Do you want graphite with no porosity, or do you want certain type of porosity? Is it acceptable for a certain application to have some porosity? Depending on that, you will do the pore filling one or multiple times. Okay, and then finally now you get your final manufactured shapes. So you understand how you can, from the raw material, already start giving the shape that you finally need. This is kind of the fundamental principle of carbon-based manufacturing. You cannot machine carbon, and you don't even try to do that, because that might actually create so many defects in your material that's not worth it. You rather just start giving shapes to the precursors and then make your carbon out of it. Okay, so yeah, whatever process I have shown in the figure, I have also, I think, written it here, so you can go through it. Okay, now there are some more details about these raw materials. You might still be wondering, what is how do we differentiate between different pitches and our cokes? What exactly is a coke? We will cover it in more detail, in further detail, during our raw materials section. Right now, I just wanted to give you an idea of the manufacturing part of it. Okay. Now, we have used in these lectures, we have used terms like calcination and burning. So here are some definitions. Burning always takes place in the presence of oxygen. Burning, in fact, is a name for oxidation. So you will always do it in the presence of oxygen or air in general, because air contains oxygen. Calcination, when you have limited to no supply of, typically you should do calcination also in the presence of air, but controlled atmosphere, controlled air. So you will not, burning is just you leave it outside, leave it in the open and let it get as much oxygen as it wants. But calcination is controlled quantity of air / oxygen. Now there is a third process which we will discuss again extensively, that is known as pyrolysis. Pyrolysis is actually the process of breaking of organic molecules, but necessarily in the absence of oxygen. So with that, I'm going to conclude today's lecture.